Hello, this section is about bandwidth and maximum data rate. We will first introduce the definition of bandwidth, and then we will look at some theories related with bandwidth. They are about the maximum data rate we can achieve on a particular channel. When we transmit digital signal on wires, the digital signal is always subject to attenuation and distortion. This is partly caused by disallowing high-frequency components to pass through. The high-frequency components are corresponding to the nth harmonics in Fourier series. Therefore, one of the definitions of the bandwidth is the range of frequency of a transmission media. It is measured as hertz, as it is about frequency. The other definition of the bandwidth is about how many bits can be transmitted within 1 second, which is measured as BPS, bit per second. From Fourier series, we can know that the large N is the higher frequency NF of the nth harmonic. The physical property determines that all transmission facilities diminish different Fourier components by different amounts. Thus, it introduces distortion. Usually, the amplitudes are transmitted undiminished from 0 up to some frequency, Fc in Hertz, with all frequencies above this cutoff frequency strongly attenuated. Therefore, the nth harmonic cannot go through the transmission media if the frequency NF is above the cutoff frequency Fc. Before we try to explain the theories about the maximum data rate, we start with some background concepts. When we are talking about distortion and attenuations, we can use a term to numerically describe a noise, which is signal-to-noise ratio. There are two ways to represent signal-to-noise ratio: S over N, in which S is the power of signal and N is the power of noise. The other representation is to use dB, which is a measurement of signal-to-noise ratio. dB is defined as 10 log 10 S over N. For example, an S over N ratio of a solvent is 30 dB. Nyquist theorem is about the maximum data rate for a given noiseless channel. The theorem defines maximum data rate as 2h log 2v bit per second, in which h is the bandwidth, v is the discrete levels. Another theorem is Shannon's theorem, which considers noise on the communication channel. The theorem is represented as maximum data rate equals to h log 2 1 plus s over n in units of bits per second, in which h again is bandwidth, S over N is signal-to-noise ratio. Note that S over N here is the ratio, not dB. Hence, if you are given signal-to-noise ratio in dB, you need to do the conversion first. Now, let's use an example to demonstrate how these two theorems can be applied for calculation. Suppose that the bandwidth of a channel is between 3 MHz and 4 MHz, and the signal-noise ratio is 24 dB. The question is, what is the capacity of this channel? Question 2, being able to achieve this maximum capacity, how many signaling levels are required? For question 1, as it is asking the maximum data rate in a channel with noise, we can apply Shannon's theorem to solve it. Therefore, the maximum data rate can be figured out as 8 Mbps. Question 2 is asking for discrete level, so we can use Nyquist theorem, and the number of discrete levels can be calculated as 16. Finally, the question to be thought about for this section, we have explained two ways of defining bandwidth. Why both Hertz and BPS can be used to describe the same bandwidth. That's it for this. Thank you very much.